And I'm back. Sorry about that. So again, the producers produce, the consumers consume, the consumers collect the breakdown materials that then go back into helping the next series of producers. There is a wonderful example of lunacy. This is potential energy. This guy dangling off this rock has the potential to fall and create and transfer a lot of energy when he smacks the bottom of the hill. Potential energy is energy that's stored. That is the definition of potential energy, stored energy, a battery. If you've got a drawer at your house filled with double A's and triple A's and D cells and C cells, all of those, while they're sitting in that drawer, they have the potential to drive reactions. So that is potential energy. Cells store and retrieve energy in metabolic reactions, and we'll talk a little bit more about metabolic reactions in a minute. Some reactions require an input of energy, others end with a release of energy. So again, we start with a product and then chemical reactions happen. Some chemical reactions will store energy, other chemical reactions will release energy. A reaction is a process of chemical change. A reactant is a molecule that enters the reaction. The product is a molecule that remains at the end of the reaction. You see chemical reactions written with an arrow. You're familiar with mathematics, 2 + 2 = 4. Well, in a chemical reaction, it will be some product plus some other product, and then there's an arrow. The arrow means yields, and then something. So the things to the left side are going to be the reactants. The things to the right side of the arrow are going to be the products. And there's energy input. You see that we are start off with a glucose molecule, or we end up with a glucose molecule that is written in reverse. You got carbon dioxide and water will come together to form glucose with a byproduct of oxygen. That oxygen then goes back into the environment to form water. And again, it is a circular product. Why Earth doesn't go up in flames. Molecules of life release energy when combined with oxygen, but not spontaneously. Energy is required to start even energy releasing reactions. You've got to put money, there's an old saying in business, you've got to spend money to make money. Same thing here. You've got to use up some energy to make some energy. And hopefully in a biological system, you use up a certain amount of energy, but you're going to make even more energy. Just like hopefully if you want to start a small business, you're going to put money in it, but you hope that at the end of the year, you've made more money than you spent. Same thing here. You want to put more, you want to start with energy, but you want to make even more. Activation energy is the minimum amount of energy needed to get a reaction going. One example of a sort of a demonstration of activation energy is starting a campfire. If you're going to start a campfire, you don't start off with a log as big around as a basketball and a match. You start off with a match and some paper or some dry grass or straw and some small pieces of wood, and you have to build a small fire to get your big log going. And that small fire would be the example of the activation energy. How much energy does it actually take to get this process going? Again, just a demonstration of reaction energy, the difference between energy of reactants and products. You start off here, you get a little activation energy, and then the energy needed to keep that reaction going goes down. Energy in, energy out. You have small molecules. You put some energy in, you make organic compounds, again, like carbohydrates, fats, and proteins. You then take those larger molecules, and as those bonds that are holding those larger molecules break, you create energy, so you got energy out. So energy in stores things, energy out uses that energy up, and you go back to very small product molecules again. Human beings, for instance, we consume products, and as we are consuming those products and as we are breathing, we produce carbon dioxide. Carbon dioxide is needed by plants to produce photosynthesis, so the plant gets bigger. And then one of the byproducts of the plant's metabolism is oxygen, the oxygen we breathe. So we are living together as one. The plants need something from us. We need something from the plants. Energy in, energy out. An enzyme is a protein or an RNA that speeds up a reaction without being changed by it. Another word that you will hear in chemistry is a catalyst. Enzymes are biological catalysts. A catalyst is something that gets a reaction going but doesn't get involved in the reaction, and it's not altered by the reaction. The classic example of an enzyme or a catalyst or an enzyme is the story or the fable of stone soup. Now, I don't know whether you've ever been told that story or not, but stone soup was a fable about a man, a beggar, who comes into a village wanting something to eat. And the people in the town won't give him anything. He comes and knocks on doors and says, I'm hungry, I haven't eaten in 3 or 4 days, and they basically slam the doors in his face. And what he does is he goes into the village square and he gets a big kettle, like a big witch's cauldron that you see at Halloween. And he puts it in the village square and he puts a bit of wood under it and he builds a fire and he gets some water from the well and he fills the pot full, or the cauldron full of, water, and he starts to heat the water up. And as the water is heating, he reaches into his bag and he takes out a little cloth wrapped bundle and he unfolds the bundle and he takes the stone and he puts it over into the water. And then he takes a big wooden spoon out of his bag and he starts to stir it. And he's stirring it. And of course, by now the people are looking out their windows going, what is this guy doing? And he continues this. And as the water warms up, he starts to taste it. And he stirs some more. And finally, after, watching this, the people start to come out and go, what is this guy doing? So they're all standing around. And finally, somebody says, man, what are you doing? And he stirs it and he goes, I'm making stone soup. And another person says, well, what does it taste like? And he said, well, it's not bad, but it would be better if it had a few onions. And somebody in the crowd says, I've got some onions. And they run home and they come back with onions. And the guy chops up the onions and puts them in the soup. And he stirs it and stirs it and stirs it, tastes it. And they said, well, how is it now? And he said, well, it's okay, but it would be better, if it had some carrots. And somebody says, I've got some carrots. And they run home and make carrots, or get carrots. And he chops up the carrots and puts them in the stone soup. And then he asks for potatoes and celery and maybe if somebody might happen to have an old ham bone that they're not using. And he winds up making this huge pot of soup. And then he tastes it and he said, oh, that's the best stone soup I've ever tasted. And then he looks and he says, wow, I've made way more stone soup than I could eat. Would anybody like some? And everybody goes, I'll take some. And everybody comes up with their bowls and he feeds the entire village from this stone soup. And as he's getting the last of the stone soup out and serving it to someone, he reaches down and he takes out the stone and he puts it back in the cloth wrapping and wraps it up very carefully and puts it back in his bag. And he says, you never know when you may need to make another pot of stone soup. The stone is the catalyst. It's the enzyme. It got everything else to happen, but at the end of the day, still had the unaltered stone. That's a catalyst or an enzyme. Substrates, reactant molecules that specifically acted upon by an enzyme. You have an enzyme in your saliva, in your mouth, called amylase. The substrate that amylase acts on is starch. Starch is broken down by the enzyme amylase. And here is how active sites on enzymes work. You see the enzyme is the green sort of Pac-Man, for those of you who remember Pac-Man. And then you have the substrates. The substrates attach at particular sites called active sites. Once they're there, they will be altered by the enzyme. You see they start off being a sort of a rusty red color. After being attached to the enzyme, they have turned to a nice little yellow color. And if you'll also notice, Here, they're two independent structures. They're two individual items, but they attach here. A reaction happens. They turn yellow, but not only did they turn yellow, but they're now fused together. That is an enzyme reaction. Each enzyme works best within a particular range of temperatures, pHs, and salts. If you go to the doctor, you're having some health issues, you're not real sure why you're feeling the way you're feeling, the doctor might take a blood sample from you, and one of the things they're going to measure is your pH of your blood. And that will tell us whether or not, and that may give us some indication of what your problem is. Hold on just a minute.